Hello everyone, we are back with another cool talk for hardwear.io webinar. Friends, we have announced 6 of our speakers who will be presenting innovative new research related to hardware security for our upcoming hardwear.io conference, which is scheduled on the 1st and 2nd of October. Do check them out. And if you are interested in any of our upcoming trainings, please do register. I will be posting the link later in the Zoom chat. Today, we have Veronica Kovah, who did her master's in computer science with a focus on cryptography and security. Previously, she worked with companies like Tesla, MITRE, SourceFire, and also with the NSA. She now runs her own security consulting firm called Dark Mentor LLC. Veronica is going to talk to us today about finding new Bluetooth low energy exploits via reverse engineering multiple vendor firmwares. For those who are new to hardwear.io webinar, if you have any questions, please use the Zoom chat window to send them across. After the presentation, Veronica will answer them. So without any delay, let's welcome Veronica to begin her presentation.
Thank you, Ant, for the introduction. And let's share my screen here. All right, can you see my screen? All right.
Yes.
Good, thank you. All right, I'm Veronica, so I don't need to further introduce myself, because Ant introduced me very well, that the information I need to share about me. Let's see. And now I'll focus on the content. So for the next 40 minutes, let me start. So 2 years ago, I really wanted to do something new that I had not been worked on before. So 2 years ago, I started researching the Bluetooth. And for the next 40 minutes, I will share my story from knowing almost nothing about the Bluetooth to finding remote code execution vulnerabilities. All right, so let's see, what does it take to start from the scratch to researching in a new area like Bluetooth? So at the very first, I start with researching the related Bluetooth security researches from different conferences. Then I started reading the Bluetooth specification. And as many of you already know, this is really large specification that has more than 3,000 pages, but I didn't need to read all of it, but I mainly focusing on the protocol parts that programmers often likely make a mistake while they're implementing it. At the very beginning, I start with the looking at the Bluetooth Classic, but then that was mid-2018, but at the beginning of 2019, I was focusing on the Bluetooth low energy. And this talk will focusing on this BLE field only. And while I was looking at the specification, just like any other specification, in many cases, the words are not clear enough. So I look for the open source implementation. And for the Bluetooth Classic, I couldn't find any, but for the BLE, I found Zephyr and Apache BleedingBit. All right. And here are the many protocols. The Bluetooth specification defines multiple protocols like here, and these protocols can be divided into 2 layers. The protocols that belong to the host, which is you can think as smartphone or the PC. These protocols always reside on the host platform. But on the other hand, there's this link layer protocol, and then the 5 layer is always end up residing on the controller device itself for performance reasons. And the spec also defines this host controller interface. So it specification defines how this HCI should be implemented in order to communicate between the host and then controller here. And this case is for the actually dual chip configuration. As you see, there is a host chip and then there is a controller chip. All right. On the other hand, for the single chip configuration, like you can often see on the IoT device, the entire these protocols end up located inside the controller device itself. And in this case, the specification actually didn't define how this HCI has to be implemented. So it is really up to the implementers. So implementer can choose, they can use either memory queue or they can choose just not to have explicit HCI layer. All right, when I started this Bluetooth research in mid 2018, there was like around, now around here, I actually counted, when I based on the public CV ID count, there were 132 CV IDs that the vulnerability has found on the upper layer protocols, but there were literally zero vulnerability has been found for the controller specific layer. But right now, actually this slide itself was made 2 months ago, but I checked 2 days ago, I count the CV IDs again. So there are 2 more CV IDs has been published, but I just didn't change this slide just because the fact that there is only 3 proven BLE RC vulnerabilities out there. Here, what I mean by the proven is whether or not a researcher actually has published the proof of concept that can overwrite program counter with an attacker controlled value. So there are vulnerabilities in this controller layer, like at 14, this one is included in the Bluetooth Classic and the BLE, but there's only 3 out there. And one is a BleedingBit, maybe some of you already have heard of, which is the company Armis founded. And 2 other, the proven RC vulnerabilities are the ones that I'm going to talk about today. All right, so now why an attacker is interested in this below HCI layer protocols? Let's say an attacker found the OS specific vulnerabilities in the Bluetooth stack, but then what attacker can do is he can only target a particular class of the devices, right? If you find on the PC, he cannot move on to the Mac because the Mac OS is different from the PC. But what about if an attacker found the vulnerability in the controller layer? The attacker can then now attack different classes of devices. It can be car, it can be just PC or the medical device, or even it can be IoT devices. So it actually extend the devices the attacker can attack and then do further more dangerous operation afterward. And today I'm going to talk about the 4 vulnerabilities, but I'm not going to very detail, but all of 4 vulnerabilities doesn't require any authentication or the pairing. So it is actually hardening at this very upfront protocol is actually quite important. And I prepared 2 demos for the 2 RC bugs. Now, let's take a look at how I actually even ended up finding this vulnerability. So as I mentioned, I didn't know anything about the Bluetooth. So first was I need to set up my lab. And here there's 2 development boards here. And in my lab, I have more than 1,000 actually development boards, but these are the only 2 development boards that I'm going to talk about today. And why I'm working with the development board instead of the end product is because it is easier to actually debug. And in the development board, actually, there is no a security actually mechanism has been implemented onto it yet. So it is easier to work on. However, at the same time, this development board is very representative to the end product. And I will show you, like here, I found a vulnerability in the ROM code. That means end product will going to have the same code. And now this was just sharing that it will be very handy for you to have in your lab is when you are familiar with the software development, the easiest way to debug is a printf. Just like that, when you work on the hardware code, like a firmware, then this UART is your basically printf. And you will need the USB to serial converters, and I do recommend to have one that has a CTS RTS line. This will save you time a lot. Right, and then you will want to have the hardware debugger. Like here, there's OpenOCD, I have it, and there's a JLink, but this one is education license one. So if you are working on this device directly, if you are also doing it as either hobbyist or you are a student, you can use this education license. However, you are doing it for profit, but make sure that you get the commercial license. And I tend to use JLink more than the OpenOCD just because it requires slightly more work to have OpenOCD work at the very beginning. But if you're familiar with this, and then there is no difference. But like me, as a hardware debugging, hardware hacking, I'm not actually a hardware hacker, but I have not done actually this low layer, then just it's easier to start with the JLink. Now, next is the USB controller. I have a fuzzer, and when you're running the fuzzer, there should be a way of power cycling with the software. So I have it this one here, and I use the UHub controller. When you check out the GitHub, it has a list of what kind of USB hub this software supports. And another one is this upper here. This is another controller with a manual button. This one actually very handy to have in your lab. And next, so now when working with this wireless, actually I found very interesting because when you send some stuff, but you don't know whether you actually send any packets or not. So you do want to have some sniffer, a way of to see actual packet has been sent or not. And I used Ubertooth and Sniffle, but there are many sniffers, so you can, I'm not just doing surveys because I'm saying that there's a lot of sniffers, but these are just the only one that I use for my work. And Ubertooth is very easy to use and have a good console display. However, this software has not been updated, so you can use this one, but if you don't have any of this, I actually recommend to have this board and use Sniffle. And actually Sniffle was introduced at the end of last year at the hardwear.io. I really appreciate that one because of that one, I found a bug in my fuzzer and I could actually fix it and I could verify it was working. And his last name was Khan, and he literally was introduced last year. All right, next. All right. And for the actual packet generation, I use the this Nordic device here. And okay, something was written. Okay, Nordic device here. And at the beginning, I start with the NRF 52832. That is just because when I check on the Zephyr and Minute, I found that there was a lot of documentation they're using this hardware. But guess what? There's because this one is an older device. That's why, always documentation works this way, right? When they write the code, then they don't make the documentation. And then usually, unless something dramatically changes, the documentation is there. So that's why there was just more documentation about this board. However, when you use this board, you have to basically connect this USB to serial converter into this single pins here. So later on, you'll find it is very cumbersome to move it around this board with attached to many lines. So later on, I found that if I use this another 50 to 840. I didn't need to this wire with a single pins, and because there is this board supports a virtual COM port, so I could use just a USB cable, one cable, and you can see the UART, debug messages. So it was way more simple. So again, if you do not have, actually this code, I would recommend you to have just 52840 dev board. That is because, hold on a second. And do you see this like a line?
Yes, I can see the green arrow.
Okay, how can I remove this one?
That should be in your annotate with an eraser or something. You should have that.
In this one here? Oh, on the tape.
Yeah.
Let's see, erase. Okay.
Yeah.
All right. So let's see. Okay, I should try not to then touch here. All right.
Yeah,
right.
it's good.
Good. So now it's right. Okay, because I was thinking. Okay, so since it was not removed, good. So I just talked about the hardware. Now you will need a software, right, to actually generate the packets. And I already released JackBNimBLE, which is a modification of Apache MyNimble. I made a slight modification. Is because Apache Nimble is supposed to be follow the specification, and he's doing great job of following the specification. But as we are looking for the vulnerability, it means we want to generate the package that doesn't comply with the specification. So I had to make some modification. So at the moment, I released this code is actually just I extracted some code from my fuzzer. So at the moment, the one that I uploaded to GitHub has a way to generate arbitrary packets for the advertisement channels. But for the data channel packets, I will release at some point, but it's not there yet, but I will release at some point. So let's see. Yeah, so, and for this one, how it works is, it comes with the two parts. One is the firmware, that is, as I mentioned, is a Apache NimBLE's modified code. And I added some custom HCI command here. So, and I have there's a host code, which is written in Python. So what happens is when you generate the arbitrary packets using this Python code, it comments to this firmware, has sent this firmware, send this packet to the victim. This is how it works. See. Now we are done with the lab setup. Let's check our victims. The first one is a Texas Instrument WL1835 mod. So this board was the very first development board I got. This supports in Boost Classic and then BLE, and this board is a development board. However, it does not have any JTAG or the serial or the SWD pins are not exposed. So it means there is no easy way to debug. But however, I found a way to debug, and I will introduce in the following slide. And this particular board, actually, for this one, I couldn't find basically firmware easily. So I end up later dumping it, the memory from this ROM. And by using actually this, there is a WL link wireless tool that is given by the TI. And you can download this one from the TI website. And it comes with many utilities, but I use the HCI tester and then the logger the most. And I will show you in the following slide. And this case of this TI device, it actually belongs to this dual chip configuration. So on this device itself, it has only this low layer protocols. And you can think as this low layer is, you can think as a SPLUZ in the Ubuntu. So, and they are communicating through the HCI layer here. And as I mentioned, I didn't have any firmware with this device. So how I dumped the memory was, there is a vendor specific command. There's a HCI vendor specific read memory. So I could see this one in the TI's documentation, and I could see the what this actual opcode is in their one of the supporting files. So I use this command on my Ubuntu and actually dump the entire memory. So I now got the firmware ROM contents handy, and I analyze using the IDA Pro. And okay, rather than reading this one, I will show you the one of the, as I mentioned, this, you know, the TI device does not have any JTAG. So the very key moment I could actually understand this in the context of the ROM content was I could identify these log functions. And there's one log function and there's a lot of wrappers, which I will show you here. And the details about how I found this log function is in the white paper, because if I go through it, it takes too much of a time. But let's say I identify this log function. So when you open this, you know, just memory dump in the IDA, you will see nothing because there's no symbols at all. So once I identified here, I could basically rename this one as this is one of the log wrappers. Basically, there's one, again, log function, and there's a bunch of wrapper functions. And after I identify this one, that this log function turns out to be basically, whenever this log function is called, it will set the level. There's a normal log level. There's from 1 to 6 for this particular TI case. And when it receives this log ID here, R0 is the log ID. And then it adds this hex 32 to 3580. It adds these values inside this wrapper function, and it expects two parameters for this format string, as you see here. How I identify it is, now I know the log function, and there is like a ILI file, I believe, yeah. There is like a list of strings. You can see this, what strings is based on this number by adding these two numbers. Then now, based on these numbers, now I see which string is being used, and I made a IDA Python script, and I labeled it, this one, in this entire format. Not entire, just places that I'm interested in. So based on this, this string log information, now I can infer, this function is lm2 perform command function name. By just repeating this process, I could understand this what ROM is actually doing here. All right, so basically, okay. All right. Now, as usual, when you do this vulnerability research, static analysis is many times not enough, because by just reading the code is hard to understand, or it is sometimes it's unclear whether you can reach that code path. So I made a fuzzer, and I could actually generate an arbitrary code, and I could actually see my code has been executed in the ROM code by patching the this binary. And I will go you a little bit more detail. Let's see. Okay, let me introduce you this one first. As I mentioned, this Bluetooth low layer protocols is located in the ROM, but there is a way you can patch it. And if you want, you can look at the Cortex M3 manual, and there is a section called a flash patch and breakpoint unit, and you will explain in very detail how you can patch this in a ROM code. And by patching the ROM, I could see what kind of register values are at the moment some code, when some code are executed. Let me get some water. Okay. And another thing I found is, while dynamically analyzing this ROM, there is actually easier to show you the photo. So this one actually show, when you hear, this is the one that I actually making the proof of the concept code. So here is like the PC value has been overwritten to 41, 41, 41. This is a thumb mode. And if somebody, some of you are familiar with this ARM, I actually override this one to 41, 41, 41, but because it's thumb mode, actually the program counter becomes an even number, right? And when you see, when I didn't patch or then I didn't manipulate this in the ROM, this is the output you see in the logger. This is a TI's utility, TI's utility. And here you don't see that much of context. What's the status of this board at the moment of crash? But as I here mentioned, I actually reverse engineered the default handler, and I found that I can. I could see. Sorry, it was just too big, too small previously. Again, I made it bigger. As you see, this was again a 41, 41, and I found that this one here memory. Hold on a second. Okay, let's go back. Let me explain about the patch one first. Okay, here. As before, this logo didn't show that much, except this one is a 41, 41. But I patched this ROM code. So the actual vulnerability is in the mem copy. So just before it hit the, the code, just before it code executed the mem copy, I actually hook the memory, so I can see what's the source address and then what's the length that is feeding into the mem copy. And this one is showing this is a source address, and the second one here, this is the length actually been feeding into the mem copy. And I will explain a bit more the disassembled assembly code in the, soon. But let's see. Next one is the one about the fault handler I just mentioned. Without changing this kind of flag, you don't see any detailed information at the moment of crash. But now I know this in a fault handler checking some flag, and if this flag is set, then it will dump all the register informations and then stack. And this photo doesn't show that, but there's a heap contents as well in the following. Now let's talk about the vulnerability in details. Actually, I found this vulnerabilities probably at the end of the 2018, but as I said, I was just studying it. So I found it because I'm familiar with the reverse engineering, but just I didn't know how to deal with this develop a Bluetooth development board. So at the time, I found the mem copy. The other mem copy, there's an integer on the floor, but I didn't know how to reach that code. And later on, I found I made a fuzzer, then found that, oh, there's a crash. Oh, and the crash actually end up then integer on the floor that I found a while ago. When actually at the time I was doing the Bluetooth classic research rather than the BLE. But anyhow, but it turns out the packet that I generate was exactly the same as a BleedingBit. And it maybe some people say, oh, I read about the BleedingBit. And this was exactly the same field. However, the code is different. In the case of a BleedingBit, vulnerability was a heap overflow, but mine is a stack overflow, which means, as you know, stack overflow is more dangerous because you can attack it more reliably than the heap. And I report this one May 22, 2019, and it was fixed in November 12th. And let's see when the attack happens. So when a device starts looking for what is it, what kind of nearby devices are there, then attacker just send, here's an advertisement. This is it, basically. As you see, there is no other, traffic is any transaction is required before attack. Basically, just a victim needs to. Just only precondition is victim should be in the state is scanning, looking for some other Bluetooth devices. You can think as you open your smartphone and then you just searching the headphone. That's it. Then attacker send a malicious packet. And now let's look at the assembly here a bit. So the first here, stack the code here is just allocate this stack memory space as a hex 2C, which is, do you remember in the one of the previous slide? Okay, maybe that's a good idea. It was I overwrote length as FC, which is FC is greater than the 2C. So I was actually overriding the stack memory. And actual vulnerability, as you see here, is the one here. R6 has the a packet length. It is a packet length field, and there is no condition before this subtraction here. So when R6 value is basically smaller than 6, then there's an integer on the floor, which means this R6 become really big number as an FFFFF. And the next instruction do is it actually do byte extension. What it means is it make zero into the 3 most significant bytes and leave only the least significant byte as it is, which becomes like a hex FC. And based on this in the calling convention, the main copy expect its length is as a R2, and source is R1, which is a heap address, and R0, as you see here, is a stack memory address. So this one ends up basically integer on the floor, leading to the stack of overflow. And this is an packet information here. An attacker can basically set the header type as 0 and the length field as a 2. And simple as that, right? And then just put, whatever the payload, 2 bytes. And why this is happen? I mentioned this when I was looking for particular place where the developer were going to make a mistake. Based on the Bluetooth specification, all the advertisement packets expect at least 6 bytes, right? So developer may think, okay, there should be 6 bytes. And based on that, assumption, they made a code, and then this kind of mistake can happen. I mean, which it should not happen anymore, but it happened. So I made the proof of concept, and then overriding the program counter with the 4141 actually was easy. But when I actually tried to make actually exploit, it was hard because of the existing background BLE traffic. So I come up with an attack scenario is a quiet place. Because of too many background traffic, I could not reliably make the exploit working. So what it means is I can DOS all the nearby devices. And there's a lot of more DOS bugs than the actually RC bugs, or even the failed RC bugs can be used as a DOS attack. So what I mean is this attacker here want to attack this device here, but there are so many nearby devices. What it can do is it can just DOS all of them and send the attack payload. However, I'm not a real attacker, and I cannot kill all my neighbors' Bluetooth devices. So what I come up with is I have a bucket. Specifically, I have a paint bucket. So I made this Faraday cage out of this paint bucket. And you just see it was not enough, so I couldn't end up tinfoil wrapping it. And here's my devices, which is wrapped with the paper and tinfoil, and this fabric is artificial fabric. So by just wrapping it up a lot, I could control the background noise. And I will show you the actual demo here. And what happens is now I have two actually different machines, and I set up my JackBNimBLE, and I send the attack from over the air. And now let's see. And if you cannot hear the audio, please let me know. And this video already have the audio included, so I'll be actually stop talking while I'm playing this video. Before launching an attack, I'm going to show you nearby BLE devices. And you don't see anything with the name pond, but one of my neighbor has a smart refrigerator. And I'm going to use btman to show HCI command and the events to just see the states of the victim. And I'm going to attach the victim device to this host. And here, as you see, the host use old patch to initialize the victim. So this device is still vulnerable. Now I'm going to command for the victim to start scanning using the HCI tool here. And launching the attack over the air from a different machine. Now you see the some HCI event, and it actually just reporting the received packets to the host. And the attack actually succeeded because when I scan nearby device again, you see pawn, but this victim is supposed to be scanning only. Right. I hope you enjoyed the demo. Okay, next one. Since I don't have enough time, I will actually skip this vulnerabilities. There's a slight difference, but if you want to know the details, please check out my white paper. And now let's see the next target, which is the Silicon Labs EFR32MG21. I picked this development board because this board supports the extended advertising packets, because I wanted to actually extend my fuzzer, and I needed a victim basically. So, but this board is actually good to debug because it has a JTAG enabled. You can actually use a GDB to debug this device, and the Bluetooth stack actually comes as a library. And very good thing is it has a symbols, so it's easy to not easy to say, but it's easier to debug. But bad side is there isn't going to be any novel reverse engineering tactics for this particular device. And this device belongs to this, as I mentioned, this single chip configuration. So entire this protocol reside on the controller device. And when I extend the make the extended advertisement packet fuzzing, I had to actually change my fuzzer a lot from especially because at the time I was using the Zephyr, but Zephyr didn't support the extended advertisement. So I switched it from Zephyr to NimBLE, and I was start fuzzing it and actually find the DOS bug almost immediately. And I fuzzing some more days, but there was nothing that's happening. So at the time I think is that really maybe the Scilab's code is very good, or my fuzzing is wrong, right? So as I mentioned, at the time I was using the Ubuntu, but I could not see whether my packet, which is has a really large packet, I couldn't see whether it's valid or not. But I was very lucky that the sniffer was introduced at the time at the end of the 2019. So I used a sniffer, and then I could actually see that when I make really large advertisement packets, it was not actually being sent. And because of that, I could actually had to debug the NimBLE, and it found that I had to actually arbitrarily increase the scheduler so that the large packet can actually be sent. So I changed NimBLE code, and I found the crash right after that. And here, as I mentioned, there's two vulnerabilities in the Scilab board. The first one is it was a DOS bug, and I will show you what this is. A memory buffer overflow. I'll go very briefly. There's an integer on the floor, and I can make this R2 value, which is a length value, really large, but I couldn't actually make it as a RC. That is because when you see here, this R2 value, there is no changes until it fit into the mem move. And before actually the device crashes, I could not have actually control this program counters value. That means this is not going to be the RC bug, but the DOS bug. The difference I was just pointed here quick is this one is actually TI code. There was, in case of TI code, there was an unsigned byte extension. So before the the chip actually crashes, I can have a little bit of control. But for this Silex case, this memo, I couldn't. So one is those bug, but the other, there was another bug that is a heap of overflow that, and as you know, heap of overflow is often complex. So I'll go very high level briefly. So when this development board received a really large packet, it actually fragmented into the smaller the buffers. And the buffer size is hex 49, which is a weird value to have the actual size of the memory chunks. But anyway, they managed this large packet into the smaller chained memory chained memory link. And while they are doing it, they made some mistakes. So I end up could overwrite from one memory chunk to the next memory chunk's metadata, and I could overwrite the memory pointer. And this is how this packet looks like. I put it as this is the extended advertisement, and this there is for the extended advertisement, there is like a nested extended header inside this payload, and I could set the value as a 3C that ends up as a crash. And without the detail, however, I will show you the cool demo that I exploit this dev board, and I make the persistent payload. And let's take a look at this one. So for this particular demo case, I'm attacking from the different machine, but there is a controller. But I just put the debugger attached to the device. As I said, this is a single chip configuration. Entire protocol is residing on this board, but I just connecting to the GDB just to check the status of the device. And here I'm remotely attacking the device and persist by building the house. So I will show you actually how the persistent work in the demo. I'm going to connect GDB to the victim device, to just see the state of the device. And the client is connecting to the GDB server. And I'm starting the Uber tools to see the BLE traffic. And I'm starting generating the malicious packets over the air from the different machine. And you see they still here advertisement. This victim is supposed to be scanning only. And this shellcode, what it does is once it exploits the device, it resets the device. And now I'm going to turn off this victim device. And it's a little bit slow because I was recording and I was typing as well. Now I'm going to clear this left lower screen in order to show that when the victim device is off, you will not see any advertisement traffic coming out of the victim device. Now I'm restarting the Overtooth. And the one you just seeing is just a random background traffic. And I'm going to turn on the device again. Now you still see this advertisement packet that proves that the exploit persists on the device. All right, I'm going to wrap up with the Bluetooth security challenges. So all the low layer device I have looked at so far, I haven't seen any actually low layer protocols have any of these mitigation techniques implemented on it. And another thing is, as I show in the demo, if an end product didn't enable this secure boot, an attacker can persist on the device. And in case of many chips out there, is frequent in the case that either it does not have a secure boot implemented at all, or this end product manufacturer didn't have it enabled, so either didn't have enabled it at all. So it is but I see the more newer chips actually have the secure boot and the secure reset, but still there's a lot of way to go. And another thing is, now I found this RC box, but then what does that mean? I was trying to assess the actual impact of it, but it was very hard because I don't know what kind of end product using these particular chips. And it can be just simple as a bulbs, or it can be a medical device. If it's a medical device, then even having those vulnerabilities can be very dangerous. And often, case of the customer list, the vendors are not going to share it because that's the company's secret. And by looking at just web searching, it's very limited that we cannot actually see the whole complete picture of what kind of end product, right, using what kind of chips out there. So this is a big challenge we need to solve somehow. But yeah, you are going to require very or chip vendors and any other Bluetooth device manufacturers their help. And you can find more information in this GitHub address here. And thank you for listening to my talk.
Thank you, Veronica. I like those two cute puppies in the last slide. Yeah, it's time for question and answers. We have few questions. Let me read them out for you.
Sure.
What is the tool which displayed all the Bluetooth logs that you used?
Oh, for the TI case?
I believe so, because this was in the middle of the presentation. Yeah. Okay.
There was when you go to the TI website, or you can search for there is a wireless tools for WL18 modules basically. So it is a Texas Instruments provided tool. So you need to actually register and then download from their website.
All right. What kind of mutation did you use for fuzzing the packets?
Mutation, I actually do kind of a very not kind of, it's still effective as I use the enumeration rather than just any specific algorithm without using it. But right. I was focusing on the fuzzing the field that developer probably gonna make a mistake. So those fields first.
All right. Can you share the link of the white paper?
White paper, sure. Or let's see. When you go here.
Okay. It's on the github.com.
On the GitHub. And there's a publication report.
All right. Yep. So yeah, I think that's it for the question and answers. Thank you so much, Veronica, and thank you so much, audience, for being part of this webinar. We will be recording this and uploading it on our YouTube channel for future references. So yeah, thank you, everybody.
Thank you. Have a good day.